Today we're going to look at a critical reading sheet. A critical reading sheet is required whenever there are multiple repairs on the system, or if we're looking at a system that you're having issues with and we're trying to figure out what is going on. If you notice at the bottom of the sheet, highlighted in red, anything marked with an asterisk are absolutely required readings. Without this information, there's no way we can determine what is going on. Zooming in to the bottom of the sheet, the required information is suction pressure, suction line temperature, liquid pressure, liquid line temperature, discharge line temperature, outdoor dry bulb, indoor entering dry bulb, indoor leaving dry bulb, entering wet bulb, leaving wet bulb. We also need the supply static pressure and the return static pressure, which adding these together will give us the total external static pressure. From here, we can look it up in the fan performance tables to determine what our indoor CFM is. We also need to know the voltage applied and the amperage while the system is running. We also need to know what speed the blower is running on. If this is an X13 constant torque motor, we need to know it's tap 1, 2, 3, 4, 5. If it is a true blown variable speed, we need to know where your tap settings are, A, B, C, D. And if it's a PSC motor, we just need to know low, medium, high speed tap. Now let's look at the system. We're given on our left box in the green an outdoor dry bulb of 85 degrees. On the right side of the screen in the box, we have an indoor entering wet bulb of 62 and an indoor entering dry bulb of 75 degrees. Now let's look at the refrigeration system. This is a 410A system. We have 125 pounds of suction, 323 pounds of head pressure. Looking at the top on our liquid line, we have a liquid line temperature of 92 degrees. Looking at the lower right, our indoor coil vapor line, we have a suction line temperature of 57 degrees. We've already taken the return and supply static pressure on this system, looked it up in our fan performance table. On medium speed tap, we have 1,930 cubic feet per minute of airflow. We also have a leaving temperature of 57 degree dry bulb and a 52.6 degree wet bulb on this system. Here we've transposed this information from the previous screen onto our critical reading sheet. This is the information that is absolutely required before you send it to us or to the factory. You do not have to do the rest of this, but if you do it, you will probably find out what is the issue is with the system on your own. Looking at our suction pressure, we have 125 pounds of suction. If we look at our temperature pressure chart, our TP chart, our saturation temperature at 125 pound suction is 43 degrees. We subtract this 43 degrees from our 57 degree suction line, and we find we have a 14 degree superheat. On our liquid pressure, going to our pressure temperature chart, 323 pounds of suction gives us a saturation temperature of 101 degrees. Our liquid line temperature is 92 degrees. So we have a liquid subcooling of 9 degrees. Also down below, we have a discharge line temperature, which is 151. Against our 101 saturation temperature on our liquid line, basically we are 50 degrees hotter on our discharge line, so we have 50 degrees of superheat on the compressor. Now let's take our indoor entering dry bulb and an indoor leaving dry bulb and subtract the difference, and we have an 18 degrees of temperature difference. Found that we had a 0.3 supply static pressure and a 0.2 static pressure on a return. These add together will give us a 0.5 static pressure. Looking up at the fan performance table for this particular air handler, We find out in these conditions we have 1,930 cubic feet per minute of airflow. We do need the supply and the return static so we can look and see if we have a well-balanced system. Moving on, we're going to plot our wet bulb and dry bulb temperatures on an enthalpy chart or look them up in an enthalpy table to find out what the heat content is of the air. Across the bottom of this chart, we have our dry bulb temperatures. The purple type lines coming across through here are our wet bulb temperatures. So we can take that dry bulb and wet bulb and plot our return temperature, take the wet bulb and dry bulb, and plot our supply temperature. These red lines are actually the heat content of the air. When we take these out on the chart, we find out that a return air has a heat content of 27.76 and our supply air has a heat content of 21.76. This is about a 6 BTU difference between the return and supply air. We take these, add them into our table, 27.76 and 21.76, and we find that we have a delta enthalpy change or heat content change of 6. We plug this into a capacity table and we find out that 6 times 4.5, which is a constant of air, times our CFM we've determined, gives us a capacity of 52,100 BTUs on this system. We also need to make sure we have down the voltage and amperage on the system and what our speed tap is. Looking at performance tables for this system, we find out at 85 degrees ambient outdoor, what we had in a 62 degree wet bulb, we should have a 310 pound head with an 8 degree subcooling. In our example, we had 323 pounds of head and a 9 degree subcooling. So we're pretty close right there. We can also look and find out these conditions. This system should be putting out 52,400 BTUs. We found and calculated we had 52,100. So we're within 300 BTUs of what this system is doing, should be doing. Looking further into the expanded service tables and zooming in on the center part of it here, we find that our conditions, 75 degrees indoor dry bulb and 62 wet bulb, with an airflow of 1,930 CFM at 85 degrees outside, we should have a liquid line pressure of 323 and a liquid line temperature of 92. That is exactly what we had, so actually we're doing perfect on this one. We should also have a suction pressure and a suction temperature of 125 pounds and 57 degrees. Overall, this system is performing right where it should be. Thank you for joining us today.